When we gaze up at the night sky, far from city lights, we become conscious of just how vast and varied the cosmos truly is. From familiar objects like the moon and the bright neighboring planet Venus, to the magnificent rings of Saturn and the distant shimmering galaxies faintly visible through telescopes. The universe teems with celestial wonders that push the boundaries of our imagination. Yet for all the marvels we see, there remain countless treasures hidden amid the stars, each possessing its own mesmerizing story of formation and cosmic evolution. One can speak of swirling gas giants, icy dwarf planets at the fringes of our solar system, or the spectacular relics of stellar explosions that shape the interstellar medium. However, there is another kind of object, somewhat intangible to the naked eye yet brimming with dynamic processes, that captivates astronomers and stargazers alike: nebulae. These vast clouds of gas and dust are often where new suns ignite and new planetary systems begin to form. Among them, the Orion Nebula stands out as a brilliant showpiece, especially for backyard astronomers, because it is one of the few nebulae visible in modest detail through small telescopes. Yet describing the Orion Nebula as merely a cloud would be an understatement. It is a veritable stellar nursery, a place where stars are born, shaped by gravity and fierce radiation. Imagine stepping into a region of space where the faint glow of excited hydrogen gas stretches light years across, and where hidden protostars, still cocooned in the swirling dust, promise the future births of entire planetary systems. This cosmic cradle, located in the sword of the constellation Orion, transcends everyday human scales of distance and time, reminding us that the universe is in a state of continuous growth and transformation. But how did we come to know about this grand cosmic tapestry of dust and glowing gas? What drew astronomers to peer deeper into Orion's epicenter? And why has it become one of the most studied and photographed objects in the night sky? The answers unfold as soon as we delve into the historical intrigue and modern investigations that have revealed the Orion Nebula's secrets. In the following sections, we will embark on a journey, both backward in time and outward into the cosmic frontier, to understand what makes this nebula so incredibly special. Allow your mind to wander as if we are gliding through interstellar space, gently approaching a swirl of violet, pink, and pale green gas. We notice subtle shapes and contours etched by stellar winds. Powerful ultraviolet radiation streams out from newborn stars, sculpting the cloud structure like a cosmic artisan. And all the while, the grand silhouette of the nebula rises from the background of the Orion constellation, beckoning us to explore. It is a sight that underscores both the fragility and the grandeur of star-forming regions throughout the galaxy. From the vantage point of Earth, we see only a fraction of its complexity, yet even this fraction is enough to inspire awe. In the heart of Orion lies an epicenter of creation, a realm where the raw material of cosmic dust and gas converges, eventually giving birth to the luminous beacons we call stars. Few phenomena in astronomy better illustrate the cycle of cosmic evolution, from nebulous clouds to brilliant suns, from ephemeral silhouettes to the shining corners of new star systems. Thus, we turn our focus to the Orion Nebula, that unforgettable cosmic cradle, to learn how it was discovered, studied, and eventually revered as one of the jewels of the night sky. Long before advanced telescopes allowed us to see the tendrils of gas in exquisite detail, ancient observers of the heavens noticed something peculiar in the constellation Orion. This pattern of stars has been recognized by various cultures worldwide, often depicted as a mighty hunter or warrior. Indeed, the bright stars Betelgeuse and Rigel anchor its corners, while the belt of three aligned stars is iconic to even casual stargazers. But just below that belt, a small cluster or sword appears, and part of this sword, the fuzzy patch, was noted to have a slightly hazy quality. Early astronomers using simple optical instruments in the 17th century began to realize that this haze was more than just faint starlight. One prominent credit for its discovery is given to French astronomer Nicolas Claude Fabry de Perez, who in 1610 is believed to have recorded the first telescopic observation of the nebula. Later in 1618, Johannes Baptista Cisatus of Lucerne similarly noted this luminous cloud. These early notes were overshadowed by more prominent names in astronomy, but they helped seed the idea that there was something unique in that patch of sky. A more formal acknowledgement came from Christian Huygens in 1656. He published the first detailed sketch of the Orion Nebula after observing it with a small refracting telescope. Huygens was astounded by the glowing region and recognized that it extended beyond what had previously been considered a cluster of stars. He famously documented the complex structure around what we now refer to as the Trapezium Cluster at the heart of the nebula. By the 18th and 19th centuries, astronomers such as Jean-Jacques Dortu de Méran, Charles Messier, and William Herschel contributed further observations. Charles Messier included the Orion Nebula in his famous catalog of deep sky objects, designating it as M42 in 1769. This helped bring attention to it among other faint nebulae and clusters in the night sky. Messier was attempting to catalog objects that might be mistaken for comets, but in the process, he recorded some of the most striking celestial bodies, including the Orion Nebula. Meanwhile, William Herschel and others were starting to grapple with the notion that nebulae might be places of star birth, an idea that was not yet well established, but hinted at the fundamental processes shaping the galaxy. Over time, improved telescopes confirmed that the Orion Nebula was not just a vague patch, but a rich, extended structure full of wisps and filaments of gas, with pockets of dust and newly forming stars. The new optical technology of the 19th century allowed astronomers to glimpse faint details, although they did not yet fully grasp the significance of star formation in such clouds. As photography advanced in the late 19th and early 20th centuries, astronomers began capturing black and white images that showcased intricate details, including the bright core, shadowy dust lanes, and faint outer loops. These images helped generate excitement around the Orion Nebula, as each improved photograph revealed new shapes and filaments. Astronomers and the general public alike were left in awe of how such an object, visible to the naked eye as a small smudge in a well-known constellation, could hide such grand complexity. By the middle of the 20th century, with the advent of spectroscopy and more refined methods of photometry, scientists began to identify the chemical makeup of the nebula. They recognized that it was composed predominantly of hydrogen, with notable presences of helium, oxygen, nitrogen, and trace elements. This marked a shift in understanding the role of nebulae as stellar nurseries, giant molecular clouds brimming with the ingredients needed for star formation. Thus, historical study of the Orion Nebula mirrors the general progression of astronomical discovery, from untrained eye to telescope, from sketches to photography, and from mere visual observation to rigorous spectroscopic analysis. Each step pulled back another layer of the cosmic tapestry, revealing how these luminous clouds are tied to the life cycle of stars. That early curiosity, whether from Perez, Huygens, Herschel, or Messier, paved the way for the deeper, more thorough understanding we have today. To appreciate the Orion Nebula, it helps to start with a few striking numbers that highlight its vast scale and physical properties. From our vantage point on Earth, the Orion Nebula sits at a distance of approximately 1,300 to 1,400 light-years away. Some measurements vary between about 1,270 in 1350, reflecting ongoing refinements in parallax measurements. In cosmic terms, that's not especially far. Our Milky Way galaxy is over 100,000 light-years across, but it is still about 7.6 quadrillion miles away if we express that distance in more Earth-friendly units. In other words, the light we see from the nebula today actually left it around the time humans were in the midst of the early Middle Ages. The Orion Nebula spans about 24 light-years across at its widest extent, though the brightest portion often noted in photographs is closer to 10 to 12 light-years in diameter. If you imagine the scale of our entire solar system, which extends a few billion kilometers out to Neptune and Pluto's domain, that dimension is tiny compared to a full light-year, which is roughly 63,240 astronomical units, or about 9.46 trillion kilometers. Therefore, the Orion Nebula is vast enough to contain tens of thousands of solar systems within its main luminous region. In terms of mass, estimates vary, but the nebula likely contains at least a few thousand solar masses of material, mostly hydrogen, H2, with traces of other elements. This mass is distributed primarily as a cold molecular cloud, with some areas ionized by high-energy photons from newly formed stars. If you were to gather all the gas and dust in this region, you could form hundreds or even thousands of stars akin to our Sun. One of the distinctive traits of the Orion Nebula is its intense emission lines, particularly the hydrogen alpha, H-alpha line, which gives it the familiar pinkish-red hue in many photographs. However, different wavelengths of light reveal different colors. In infrared, the dust glows in subtle patterns, unveiling hidden protostars that are invisible in optical wavelengths. In ultraviolet, powerful radiation streams from the Trapezium Cluster and other hot young stars, ionizing the surrounding hydrogen gas and causing it to emit a characteristic red or pink glow. Greenish glows can occur due to doubly ionized oxygen lines, often referred to in amateur astrophotography circles as forbidden oxygen emission lines, though the term forbidden is a specific quantum mechanical reference rather than an indicator of cosmic taboo. Comparisons with Earth give us a sense of scale that borders on the fantastical. If we imagine transporting our planet to the Orion Nebula, it would be utterly dwarfed by the swirling gas and dust. The entire Earth-Moon system would be little more than a speck. Even if we place the entire orbit of Jupiter or Saturn inside the Orion Nebula, it would vanish in comparison to the nebula's luminous volume. In essence, we are dealing with an environment on a scale so immense that our everyday mental yardsticks become almost meaningless. Yet it is not simply size that defines the nebula's identity, but also its role in star formation. Astronomers classify Orion as the nearest massive star-forming region to Earth. Because of its relative closeness, it provides a crucial laboratory for studying the processes that give rise to new stars and potentially entire planetary systems. While other notable nebulae, like the Carina Nebula or the Eagle Nebula, may be more dramatic in certain respects, the Orion Nebula's prominence in the sky and its short distance from us make it an object of intense scientific focus. Thus, we have a sense of what sets the Orion Nebula apart. It is immense, it is active, and it is accessible in terms of astronomical observation. These factors combine to make it a cornerstone in the field of astrophysics, bridging the gap between local cosmic scales and grand galaxy-wide processes. Understanding the Orion Nebula is akin to piecing together a cosmic puzzle that can help us grasp the formation of our own sun and the entire star population that lights up the night sky. When discussing a nebula, the term internal structure differs from how we might describe the layers of a planet, like crust, mantle, core. Here, it's more about the distribution of gas and dust, the presence of local knots of higher density, and the arrangement of newly forming stars. One can visualize the Orion Nebula as part of a larger complex known as the Orion Molecular Cloud, a vast region of interstellar material that extends for hundreds of light years and includes several star-forming sites, e.g. Barnard's Loop, the Horsehead Nebula, and the Flame Nebula. Within the bright central region of the Orion Nebula, there are several key components. The Trapezium Cluster. At the very heart of the nebula, a group of 4 primary stars with additional dim companions form a trapezoidal arrangement easily discernible in moderate telescopes. These massive hot O and B-type stars pump out intense ultraviolet radiation, ionizing the surrounding hydrogen and creating a brilliant emission region. The fierce stellar winds from these stars also carve out cavities, shaping the nebulous gas into arcs and filaments. Ionization front. The boundary between ionized gas, periodontary H2 region, and neutral colder material molecular gas is a defining feature of the Orion Nebula. This front is where energetic photons from hot stars collide with the cooler, denser gas. The interplay results in a sharply defined region glowing at specific wavelengths. Proplyds, protoplanetary disks. Perhaps one of the most fascinating aspects of the Orion Nebula is the presence of hundreds of proplyds, small disc-shaped regions of gas and dust orbiting young stars. These are believed to be embryonic planetary systems in the making. Many of these proplyds are silhouetted against the bright nebular background and are subject to intense photoevaporation from the trapezium stars. They serve as direct evidence that star formation is ongoing, along with the potential birth of new planets. Dark dust lanes. Interspersed through the nebula's luminous portions are denser pockets of dust that absorb visible light, creating intricate dark shapes. These lanes are more transparent at infrared wavelengths, which is why instruments like the Hubble Space Telescope, with near-infrared capabilities, and the James Webb Space Telescope can peer deeper into these dusty regions to discover hidden stars. Outflows and jets. Young stars can exhibit energetic outflows, collimated jets of gas that stream outward at high speeds, eventually colliding with surrounding material. This interaction forms Herbig-Haro objects, bright patches or knots that signal active stellar birth. Within the Orion Nebula, researchers have detected numerous such jets, reinforcing the picture of a dynamic, changing environment. Temperatures within the ionized regions can reach 10,000 Kelvin or more, though the neutral molecular cloud remains at much cooler levels, just a few tens of Kelvin. These thermal gradients, along with variations in density, fuel complex chemical processes and shape the ongoing star formation. Astronomers believe that the region has been forming stars for at least a few million years, and it continues to do so. This timeline may seem immense by human standards, but in cosmic terms, it is still relatively brief, just a blink in the 13.8 billion year history of the universe. Moreover, the Orion Nebula's magnetic fields and turbulent gas flows introduce additional layers of complexity. Magnetic fields can slow or guide the collapse of gas clouds, while turbulence can either hinder or enhance star formation depending on local conditions. Researchers rely on sophisticated simulations and high-resolution radio or sub-millimeter observations, e.g., with the Atacama Large Millimeter, Submillimeter Array, ALMA, to unravel these processes. Each new observation or computational model refines our understanding of how giant clouds ultimately become luminous star clusters. To put all this into perspective, imagine standing inside a cathedral of cosmic dust and light. You see columns of glowing gas rising into vaulting arches of darker molecular material. The floor is strewn with pockets where newborn stars huddle amid swirling protoplanetary disks, forming the seeds of future solar systems. It is a process both violent and gentle. Violent in the sense that stellar winds and radiation can be ferocious. Gentle in the sense that the gravitational coalescence of material unfolds gracefully over hundreds of thousands of years. This intricate anatomy of the Orion Nebula is more akin to a living ecosystem than a static structure. Stellar feedback influences star formation patterns, which in turn modifies the cloud's density distribution, which then shapes the environment for the next generation of stars. In sum, the internal structure of the Orion Nebula stands as a testament to nature's capacity for complexity and creativity at scales that far surpass human experience. Throughout centuries of astronomic endeavor, the Orion Nebula has been a prime target for upgrades in observational technology. Galileo Galilei himself may have glimpsed the region, though no formal record of him identifying it as a nebula exists. And subsequent pioneers like Huygens built progressively better telescopes to peer deeper into the glowing cloud. Moving into the 20th century, large ground-based telescopes, such as the 100-inch Hooker telescope at Mount Wilson Observatory, and later the 200-inch Hale telescope at Palomar Observatory, permitted more detailed studies. Astronomers were captivated by the unusual brightness and structure of the Orion Nebula, which set it apart from other nebulae in Messier's catalog. Spectroscopic analysis in this era confirmed the strong emission lines of hydrogen, helium, and heavier elements like nitrogen and oxygen. Researchers also began noticing radial velocity shifts in certain filaments, indicating that pockets of gas were moving at high speeds, possibly due to stellar winds or jets. A major leap came in the space age, beginning in the 1960s and 1970s, when observatories could detect radio waves, infrared, and ultraviolet emissions. The Infrared Astronomical Satellite, IRAS, in 1983 probed the nebula's cool dust, revealing a wealth of hidden stellar embryos. Ground-based interferometers specialized in submillimeter wavelengths also contributed, exposing molecular lines like CO, HCN, CS that indicated active chemical networks in the dense clouds. Then in 1990, the Hubble Space Telescope was launched, revolutionizing our view of the cosmos. Hubble's keen optical and near-infrared vision delivered some of the most iconic images of the Orion Nebula, unveiling proplyds, bow shocks, and intricate filaments in stunning clarity. For the first time, the wider public could see a crisp image capturing thousands of stars at various stages of formation, many still embedded in their natal cocoons. The Spitzer Space Telescope, operational from 2003 to 2020, further enriched our perspective with its infrared sensitivity, detecting the glow from dust grains warmed by young stars. Meanwhile, the Chandra X-ray Observatory mapped high-energy processes in the region, pinpointing flaring T-Tauri stars and massive, energetic O-type stars that produce intense X-ray emissions. In the 21st century, ground-based facilities like ALMA, Atacama Large Millimeter Submillimeter Array, in Chile provided unprecedented resolution in submillimeter wavelengths, allowing astronomers to trace the motion and distribution of cold, dense gas with amazing precision. ALMA's data confirmed the presence of complex organic molecules in certain hotspots, fueling debates about the potential for prebiotic chemistry in star-forming regions. The story continues with the recent launch of the James Webb Space Telescope, JWST, which boasts sophisticated near-infrared and mid-infrared instrumentation. Early images of the Orion Nebula from JWST highlight previously hidden structures in protoplanetary disks, outline the morphology of outflows with fresh detail, and illuminate the interplay between newborn stars and their environment. The combined data from JWST, Hubble, and ALMA represent a synergy that drives forward our grasp of stellar birth, planetary disk evolution, and nebular chemistry like never before. Hence, the Orion Nebula's research history is a microcosm of astronomy's progress. Each new observational tool, be it a bigger ground telescope, a specialized space observatory, or a more sensitive spectrometer, reveals fresh layers of complexity. For centuries, the nebula has invited scientists to refine technology and theories, and it has rewarded them with surprising discoveries that continually reshape our understanding of the cosmos. A single photograph of the Orion Nebula often brims with recognizable features that have been named, measured, and studied extensively. Let's embark on a virtual journey across some of the nebula's key landmarks. What's known as the Trapezium Cluster is often considered the heart of the nebula. The brightest stars here, labeled A, B, C, D, and beyond, emit radiation so powerful that it sculpts the surrounding gas. In visible light, the region is a tumult of swirling structures. The trapezium itself fits within a space roughly a few light days across, yet it influences a region many light years wide. At the center lies Theta 1 Orionis C, an O-type star more than 30 times the mass of the Sun. Such stars burn brightly and live short, intense lives, pumping out streams of charged particles that shape the nebula's future. Next, there's a feature called the dark bay, or the fish's mouth. When you look at a typical long-exposure photograph of the Orion Nebula, a dark, curving bay, or indentation, can be seen near the bright central region. This is a dust-laden swath that blocks optical light, creating the appearance of a cavity or mouth. In astrophotographs, this bay is one of the most striking contrasts, giving the nebula its iconic look. Just beneath that lies what astronomers refer to as the bright bar. It's a luminous region known as the bright bar, an ionization front illuminated by ultraviolet radiation from the hot stars. Detailed spectroscopic studies of the bright bar have revealed gradients in temperature and density that are crucial for understanding how stellar radiation carves into the molecular cloud. Further out, we have what's called the Orion Sword region. Visually, the nebula is part of Orion's sword, which also includes M43, a smaller but closely related patch of glowing gas just north of the main nebula, and other fainter segments. M43 was once considered part of M42, but is separated visually by a thin dark lane. This region in total presents a mosaic of emission and reflection nebulae, adding texture to the overall scene. Scattered throughout are objects known as proplyds. As mentioned before, these are protoplanetary disks orbiting young stars. Some proplyds appear as tadpole-like shapes with heads pointed toward the trapezium stars, indicating how stellar winds are eroding the outer layers. They range in size from tens to hundreds of astronomical units, comparable to or larger than our solar system's outer reaches. Some of them display jets or outflows, turning them into miniature, ephemeral sculptures that highlight how stars and potential planetary systems form in a high-energy environment. Then there are the reflection nebula components. While Orion is predominantly an emission nebula, where gas is excited to emit its own light, there are also regions where dust reflects the light from nearby stars, creating reflection nebulae. These areas often manifest in a bluish hue in processed color images, contrasting with the pink or red emission from ionized hydrogen. Zooming out, we encounter the Orion molecular cloud complex. Beyond the bright optical region, there are large extended areas of neutral and molecular gas, shaped into arcs like Bernard's loop. Though not fully visible in typical Orion Nebula images, they represent a larger ecosystem of star formation. This complex extends much farther than M42 itself, linking it to other famous structures, such as the Horsehead Nebula and the Flame Nebula, also in Orion's constellation region. Temperatures across these features can range from a few tens of Kelvin, deep in the dusty cores, to over 10,000 Kelvin in the ionized zones, emphasizing how swiftly conditions change with proximity to massive, luminous stars. In purely aesthetic terms, each region presents a colorful tableau, from bright pinkish-red emission lines to subtle grayish-brown dust lanes. The effect is that of otherworldly beauty that enthralls both amateur astrophotographers and professional astronomers. In comparing the Orion Nebula's topography to something on Earth, we might conjure images of Grand Canyon-sized trenches or swirling cloud formations reminiscent of violent weather systems. Yet the scales are so immense, stretching over light years, that it's hard to translate these cosmic landscapes into terrestrial analogies. The best we can do is note how each feature is shaped by interactions between radiation, gas, dust, and gravity. Everything is in flux, changing over tens of thousands of years, but still offering a snapshot of star birth in action. While a nebula does not have an atmosphere in the same sense a planet does, we can still talk about the environmental conditions or climate that prevail. The Orion Nebula is a textbook example of an H2 region, a cloud of ionized hydrogen heated by young, hot stars. The densities in such a region can vary from hundreds to thousands of particles per cubic centimeter, which is still incredibly tenuous by Earth standards, but dense compared to typical interstellar space. Let's start with the gas composition, dominated by hydrogen over 90%, with helium making up most of the remainder. Trace amounts of oxygen, nitrogen, sulfur, neon, and other elements are also present. These heavier elements can become ionized or remain neutral depending on local conditions. Emission lines from these atoms and ions produce the rich spectra that astronomers measure. Now let's talk about pressure and density. The pressure inside the nebula is not uniform. Regions closer to the massive stars experience higher energy flux, increasing local ionization and temperature, thereby affecting the pressure balance. Further out, cooler molecular gas remains less disturbed. The pressure differences drive flows of gas outward. Then there's the radiation field. The ultraviolet light from O-type and B-type stars blasts out in all directions, ionizing hydrogen and creating a bright emission zone. This radiation field sculpts the edges of denser clumps of gas, leading to stark ionization fronts and photodissociation regions. Strong magnetic fields and cosmic rays add further layers of complexity to the local climate. Let's not forget about winds and turbulence. Stellar winds from massive stars can reach speeds of hundreds or thousands of kilometers per second. When these winds collide with denser pockets of gas, they create shock fronts, compressing the gas and sometimes triggering new bursts of star formation. Alternatively, the turbulence can disrupt nascent star-forming clumps, depending on the interplay of forces. As for temperature variations, those are dramatic. Temperatures in the ionized region can climb to around 10,000 Kelvin, while dusty cores or filaments overshadowed by thick material can be as cold as 20 Kelvin or lower. This radical difference over relatively small spatial scales fosters a dynamic weather pattern on cosmic timescales. You could say the Orion Nebula hosts storms of charged particles, shock waves, and intense photon flux, but spread out over distances and times that dwarf our terrestrial frame of reference. Compared to Earth's atmosphere, the Orion Nebula is almost a vacuum, far less dense and structured. However, climate in the cosmic sense refers to how radiation, turbulence, and gravity interplay to shape the evolving environment. If you imagine yourself drifting through the nebula, you might see streams of glowing gas over immense distances, dotted by dark lumps that obscure bright stars. Occasionally, you'd witness glowing shock fronts, like ephemeral auroras on a grand scale, caused by colliding flows. All these phenomena highlight the dynamic nature of star-forming regions, turning them into veritable cosmic laboratories for physics, chemistry, and emergent complexity. Many giant molecular clouds are scattered throughout the Milky Way, and a number of them host star formation. Yet the Orion Nebula holds a privileged position in our understanding of stellar nurseries, owing to several factors. At around 1,300 to 1,400 light-years away, Orion is one of the nearest places where massive stars are forming. Its relative closeness allows astronomers to achieve higher resolution in their observations, making it an excellent test case for studying star formation mechanisms. The presence of massive O and B stars in the Trapezium Cluster means the nebula is bathed in intense ultraviolet radiation. This radiation not only illuminates the surrounding gas, but also ionizes large volumes of hydrogen, resulting in bright emission. That's partly why the Orion Nebula is visible to the naked eye under good conditions and stands out even more vividly in telescopic or photographic views. The Orion Nebula region includes everything from massive, short-lived stars to modest sun-like stars, and even low-mass objects that might be classified as brown dwarfs. This diversity provides a comprehensive snapshot of how stars of different masses form and evolve in the same neighborhood. The abundance of proplyds is a hallmark, offering direct observational proof of planet-forming disks. Researchers can track how these disks change under strong radiation fields. Not every nebula offers such an up-close and personal look at the earliest stages of planetary system formation. Observations from radio to optical frequencies show complex chemical processes at work. Molecules like carbon monoxide, CO, formaldehyde, or H2CO, methanol, CH3OH, and others exist in the molecular cloud, hinting that the Orion Nebula fosters a fertile environment for chemical pathways that could be relevant to prebiotic chemistry. Stellar winds, supernova remnants in the broader Orion region from earlier generations of massive stars, and large-scale flows of gas converge, making it a region of constant shaping and reshaping. This dynamism reveals cosmic processes that have shaped not just Orion, but presumably many star-forming regions, including the one that gave birth to our own sun about 4.6 billion years ago. In essence, the Orion Nebula is unique not simply because it's bright or nearby, but because it demonstrates in real time how stars and planetary systems come into being. Each new generation of instruments that targets Orion yields additional layers of insight. The synergy of closeness, intense radiation, and variety in stellar population transforms the nebula into a fundamental laboratory for astrophysical theories. It's worth noting that our vantage point is an essential part of the story. Because Orion lies within our galactic neighborhood, we can observe details that would be impossible to resolve in more distant star-forming regions. This vantage allows us to say, it's thanks to Orion that we understand star formation as well as we do. Indeed, many phenomena discovered in Orion have served as a blueprint for interpreting the behavior of more distant, less easily observed nebulae scattered throughout the Milky Way and beyond. Even after centuries of study, there's still much to learn about the Orion Nebula. Modern observatories, both in space and on Earth, continue to refine our understanding. Launched on December 25, 2021, JWST's cutting-edge instruments allow astronomers to penetrate dust-shrouded regions at near-infrared and mid-infrared wavelengths. Its higher resolution and sensitivity compared to previous telescopes will open up an unprecedented view of proplyds, jets, and the chemical complexity within the nebula. Researchers anticipate new revelations on the formation rates of protostars and the evolution of protoplanetary disks under intense radiation fields. Over the next decade, facilities such as the European Extremely Large Telescope, EELT, the 30-meter telescope, TMT, and the Giant Magellan Telescope, GMT, are set to revolutionize ground-based astronomy. Equipped with advanced adaptive optics, these gargantuan mirrors will attain resolutions that rival space telescopes, but with greater light-gathering power. The Orion Nebula will be a prime target for such instruments, allowing for spectroscopy of individual proplyds and faint filaments. Arrays like ALMA, already operational, and the next-generation Very Large Array, NGVLA, proposed, can detect the faint radio and submillimeter signatures of molecules within star-forming cores. For the Orion Nebula, future expansions in radio observations will clarify how gas collapses into stars, how jets evolve, and whether significant complex organic molecules are forming in these newly born systems. While not typically pointed at star-forming regions as prime targets, the boom in the small satellites with specialized instruments might open up new ways of monitoring time-variant phenomena, like flares from young stars or ephemeral structures in the nebula's outskirts. Sending a spacecraft physically to the Orion Nebula is far beyond our current or near-future capabilities. It's more than 1,000 light-years away, so any direct probe would take millennia, even at a significant fraction of the speed of light. However, some advanced mission concepts for interstellar travel exist at theoretical levels, e.g., solar sails accelerated by powerful lasers. These concepts, while purely speculative at present, serve to expand our imagination about how we might one day approach star-forming regions in situ. For now, remote sensing from telescopes remains our best and only portal. The overarching theme is that Orion remains front and center in the quest to answer fundamental questions. How do stars of various masses form? How do planetary systems emerge and survive intense radiation? What role do magnetic fields and turbulence play in shaping stellar nurseries? As technology advances, each new vantage point or observational technique promises to refine or challenge our existing theories. The excitement surrounding future missions underscores a broader perspective. The Orion Nebula isn't just an isolated curiosity, it's a critical piece of a universal puzzle. By understanding Orion, we glean insights into the broader processes that have governed star birth in galaxies over cosmic time. Each generation of telescopes peels back another layer, revealing new wonders and complexities that remind us how far we have come and how far we still have to go. Standing back from the minutiae of data and technology, we arrive at the bigger picture. The Orion Nebula is a cradle of stars, an astronomical treasure where the universe's grand design is on full display. Its glowing gas, brimming with potential, encapsulates the processes that have led to countless stars and possibly planets throughout our galaxy. One cannot help but think of our own solar system's origins. About 4.6 billion years ago, a similarly dense cloud of gas and dust collapsed to form the Sun and the surrounding planetary disk. Our cosmic home was once like one of Orion's hidden proplyds, a place of swirling dust that eventually gave rise to Earth and the conditions for life. Why does this matter for humanity today? The Orion Nebula exemplifies the stellar life cycle, from cold molecular gas to newborn stars, from star formation to the inevitable supernovae that recycle heavier elements back into the interstellar medium. We, as human beings, are part of that grand cycle. The carbon in our bodies, the oxygen we breathe, the iron in our blood, much of it was forged in stellar furnaces billions of years ago. Observing regions like Orion helps us trace the cosmic origins of the elements that make up our world. Moreover, the ongoing exploration of Orion through telescopes like Hubble, JWST, and numerous ground-based facilities reminds us that we are never done learning. Each discovery opens new questions. Each refined instrument offers deeper insights. The legacy of curious observers, from Peiresc and Huygens to modern astrophysicists, has brought us to a place where we can confidently chart star formation down to remarkable detail. In a broader sense, the Orion Nebula study ties into the search for life beyond Earth. The Pleiades and nascent systems we see may one day host habitable worlds. While life itself is an incredibly complex phenomenon, it emerges from the interplay of chemistry, temperature, radiation, and time. Understanding the conditions in Orion's star-forming regions offers a glimpse into how widely such environments might occur in the galaxy. And if we find that the processes in Orion are common, it raises the hope that countless star systems could host planetary surfaces where life in all its diverse forms might blossom. Finally, the sheer wonder evoked by looking upon Orion cannot be understated. To see a faint smudge in the constellation Sword, and to know that it is, in reality, a seething cauldron of cosmic creation spanning light years, is a humbling experience. It challenges us to expand our perspective beyond earthly concerns and see ourselves as part of a vast tapestry. Thus, in reflecting on the Orion Nebula, we stand at the crossroads of scientific inquiry, philosophical introspection, and imaginative possibility. We hold in one hand the data and theories that decode star formation, in the other, the human spirit that yearns for exploration. The synergy of these impulses drives our fascination with the universe and our quest to uncover its mysteries. If we can learn so much from one nearby stellar nursery, imagine what else awaits us in the countless other nebulae that fill the Milky Way and beyond. In the end, the Orion Nebula remains both a teacher and a muse. It teaches us about the engines of cosmic creation, guiding our understanding of astrophysical processes that shape galaxies. It also inspires us to dream of voyages to the stars, to wonder about cosmic neighbors, and to cherish our own fragile planet as a product of these wondrous processes. If there is one conclusion we can draw, it is that our exploration of Orion and of the cosmos at large is only beginning. Day by day, mission by mission, insight by insight, we piece together the story of how the universe evolves, reminding ourselves that we too are stardust returning its gaze to the skies above.